Section 9.2 starts on exponential functions. Functions, of course, you see things like f of x equals, for instance, maybe x plus 3 or x squared plus 3. We have practiced graphing these parabolas, and when you graph, the easiest way is to just plug in numbers, like make an xy chart, say x is 0, then y would be 0, if x is, y would be 3, if x is 1, 1 squared is 1, 1 plus 3 is 4, if x is negative 1, so on. An exponential function is, even though this 2 is an exponent here, an exponential function is when you have that number switched. So let's say 2 to the x. So your variable is actually in your exponent. That's what makes this an exponential function. Well, what is that going to look like? Let's graph this. If we make an xy chart, let's say if x is 1, well then y is 2 to the first. It's because we put the 1 in for x, so that means y would be 2. So there's 1 point, 1 comma 2. What if x was 2? Well, that would be 2 squared, so that means 4. If x is 3, then that would be 2 to the third, and that's 8. And let's go the other way. What if x was 0? Remember that 2 to the 0, anything to a 0 power is 1, so 2 to the 0 is 1. If x is negative 1, that means 2 to the negative 1, or 1/2, because the negative tells you to flip this. This would be 2 to the negative 2. That would be 1 over 4. All right, so let's take a look at those numbers and graph them. So we have at 1, comma 2, so 1, comma 2, 2, comma 4, 3, comma 8, 4, 5, 6, 7, 8, and we'll go the other way. At 0, that's 1, negative 1, 1/2, negative 2, 1/4. Let me just write those, label my graph, 2, 4, 6, 8. So as you can see, this number is going to go really high really fast, and it's also going to go way over here. It's never going to cross this line because let's say I put in negative 10. Well, that's just 2 to the negative 10, or 1 over 2 to the 10th. That is not a number that's less than 0. So we're actually never going to go less than this line. That is a basic exponential function. On that same graph, let's take a look and see what happens if I graph f of x equals 3 to the x. What might happen if I increased this base number? So we'll say x and y. If x is 0, well then 3 to the 0 would be 1, because anything to 0 power is 1. If it's 3 to the first, that's 2. 3 squared would be 9. 3 cubed would be 27. That gets to be a really big number very fast. So let's go the other way. 3 to the negative 1 would be 1/3. Negative 2, 3 to the negative 2 would be 1/9. So let's just plot that. Have the same graph here. 1, comma 3. Sorry, that should be a 3. 1, comma 3, 2, comma 9. So what you see is actually it gets steeper faster, and it gets smaller faster. So increasing this number just shifts my graph over in a certain direction. Now let's take a look. If you had f of x is equal to now 1/2 to the x. What do you think might happen here? So here's x and y. Well, if x is 0, 1/2 to the 0 power, that's always just 1. Anything to a 0 power is 1. If I put in 1, that's equal to 1/2. If I square it, 1/2 times 1/2 is 1/4. If I cube it, 1/2 times 1/2 times 1/2 is 1/8. Well, we're getting smaller, so let's go in the other direction. If I put in a negative 1, that's 1/2 to a negative 1 power. Remember, that flips my fraction, so that's actually 2 to the first, or just 2. If I plug in a negative 2, that's 4. I flip it and square it, so that's 4. Negative 3, 1/2 to the negative 3rd power would be 8. What has that done? It looks like it has flipped my graph to the other side. So we have 0, 1, same place. 1, 1/2, 1, 1/2, 2, 1/4, 3, 1/8. Looks like it's getting small. Then we have -1, comma 2, -2, comma 4, -3, 8. So it looks like when I put this into a fraction, that actually flips my graph to the other side, so I actually come from the top and then go down to the bottom. Now, look what happens. Remember when we do inverse functions, like we did in the last section, if I had f of x was equal to 2 to the x, and we'll just switch this with y, because that's what we do, what do you think might happen if I switched my x and my y? Well, I would have to solve, if I was going to solve for y, like take the y root of x, and that's some math that we haven't really gotten to yet. We're going to get to it soon. But instead of solving for y and finding what the inverse function of x is, because that's what we're doing, why don't we just graph this the way it is? If x equals 2y, well, I could plug something in for x, like 0, but I have no idea what could make that 0. What am I going to put to a power that's going to make that 0? So why don't we go the other way that we normally do? Why don't we start putting y in for 0? So 2 to the 0 is equal to 1. 2 to the first, if I plug 1 in for y, then this would be 2 to the first, which equals 2. If I plug in a 2, that's 2 to the second, which is equal to 4. If I plug in a 3, 2 to the third equals 8. It looks a lot like we were just doing before. If I plug in a -1, 2 to the -1 is equal to 1/2. 2 to the -2 is equal to 1/4. So let's graph. That's 1, 0, 2, 1, 4, 2, 8, 3, 6, 7, 8. And if I go the other way, 1/2, -1, here, here, and that is what my graph is going to look like. So this would be the inverse of this graph up here. Up here we have 2 to the x in black, and here we have x equals 2 to the y. So flipping those numbers, instead of solving for y, I'm just going to plug it in the way it is, get my points. This is now 2, 1, 4, 2, and I just graph like I normally do. Let's take a look at how this might apply to a real-life situation. So exponential functions are used when things grow very, very quickly, like a population. Let's say you have 2 people, and they have 4 kids. So here's dad, here's mom. They have square, square, circle, circle. There's 2 boys, 2 girls. What if each of them had 4 kids after they married other people? This guy would have 1, 2, 3, 4 kids. This guy would have 1, 2, 3, 4 kids. This would have 1, 2, 3, 4. This one would have 1, 2, 3, 4. So going from 2 people in the first generation, 4 people, it's not that it adds 2 every time. It actually multiplies by 2. It's actually a power of 2. Because this is 2 people. There's 4 people. There's 4, 4, 4, and 4. That's 16 people, right? So this increases by a big amount, and that's how population growth is. So let's look very quickly at number 39 in your book. So number 39 says the world population in billions of years, 2 years after 1980, can be approximated by this equation. So I'm just going to write that down. 39 would be P of t equals 4.495 times 1.015 times t. This is actually the number of people there were in 1980, so 4.495 billion. And t is t years after 1980. Part A says to predict what the population would be in 2008. Well, 2008 is how many years after 1980? We would just subtract. So it is 28 years, which would equal t. We're going to plug that 28 in up here. Take this to a power of 28, multiply this, so P of 28 would equal some number. All right, and then it also asks you to graph the fraction. Not too difficult. The word problems are just seeing how you can apply this information. Now this actually pertains to real life. That is it for 9.2. Good luck.